who leads the Knowledge Discovery Lab at the GE Global Research Center in Niskayuna, New York. I hope I pronounced that right. In that role, and also as a former member of the Machine Learning Lab and Computational Intelligence Lab, Steve develops and applies advanced AI and machine learning algorithms for complex problem solving. He holds a PhD in computer science from the University of Nottingham in the UK, and also holds degrees from Kansas State University. In the UK at Nottingham, he was a research fellow in the Automated Scheduling, Optimization, and Planning Research Group. Dr. Gustafson is also technical editor-in-chief of the journal Mimetic Computing, and in 2006, he received the IEEE Intelligence Systems AI's 10 to Watch Award. Today, he'll be talking about leveraging AI for big industrial data science. The talk will present an overview of the industrial internet as well as several unique technologies developed to bring structured domain knowledge to data management in industry. The talk will last about 30 minutes or so, maybe a little longer, and then there'll be time for Q&A at the end. And we ask that you type your questions into the chat box as we go along, and then we'll hold the questions to the end and give Steve a chance to answer them then. So once again, thanks for attending, and welcome, Steve.
Hi, thank you so much for the introduction. So it's my pleasure to be here today, and I thank the NCDS organization for hosting this. I am a very passionate person about artificial intelligence. It's what drove me into graduate school, and I'll speak more about that later. And I'm very excited over the last few years to see the interest in the escalation of activity in the big data space, data science, and then now artificial intelligence. And they're all sort of folding back on themselves on each other to, I think, really change industry and change the world and drive some very meaningful impact. So today I'm joining you from the headquarters of General Electric Global Research in upstate New York near Albany. It's a beautiful spring day, and I'll say just a few things about where I'm coming from. I've been at the center almost 10 years, and I lead a team of scientists in the space of knowledge discovery, including both the logic, knowledge representation, reasoning aspects, as well as some data mining areas around big data systems, research, text mining, NLP. And our goal or our mission as a lab is to capture the knowledge of the organization and turn it into meaningful products or meaningful tools for our customers and for our GE businesses to provide value to the GE customers. And so in that sense, we're very much an applied research organization, and I work within an organization of many great technologists and scientists and labs, and with about 2,000 scientists here and another 1,000 distributed around the world at several locations. And I'll conclude the introduction, kind of general introduction, by mentioning this massive effort, an initiative that GE started a few years ago. And you can find out a lot today by just simply Googling GE software. It started with creating a center in the Bay Area to hold experts and leadership around software and start to build a game-changing industrial platform called Predix. And today there's a lot of information available and all sorts of partnerships that are coming out of that. And then the other thing that was initiated a few years ago, which is now coming to a really interesting place, is the Industrial Internet Consortium. And that term, Industrial Internet, is what we call that sort of networking of machines and people for industry scale applications. Earlier in the 7th series, Russ from Cisco gave a great talk around the Internet of Things with the perspective that he and the organization brings. And so I won't go into details about IoT and what that means. I'll just mention a few highlights there. But this is a fundamental shift, and it's an extremely exciting time. And I'm having a lot of fun working at the GE company, looking at how technology can help this vision come to fruition. So that's a little bit about myself. I think before I go on, if you can put yourself on mute, I'm getting a little feedback that hopefully isn't getting to other people as well. Okay, so and the last thing I'll say is, please feel free to reach out and connect with me on Twitter, on LinkedIn, and of course, I'm sure my email is out there as well. So let me start just by kind of motivating why we're talking about data science today. I know that the last two talks have introed it, and I'm sure everybody here has heard of many, heard presentations about data science and applications and opportunities. But I want to give you the industrial perspective, which I think is very meaningful, and it's different, and it changes the way I think you think about this. And really, what I hope, the goal of this webinar is, if I just go back to the title slide, is I want to stress two topics: the importance of knowledge and the importance of explanation in data science. And we're trying to address those two topics using artificial intelligence. And that's really, the goal, and I'll come back to that in some detail in just a minute, but I want to first motivate or introduce my perspective. So when I came to GE, I came from doing my PhD and postdoc at the University of Nottingham, and what I was doing there was I was investigating algorithms, machine learning algorithms, to help learn models and patterns from data that could be inspected and understood. And when I came here, I came here under the auspices to look at data from aircraft engines and similar machines and do a task called feature construction. So that's a very typical task in machine learning. But the idea was that at the time there wasn't, there was a lot of data, but there wasn't a lot of features available, and the machine learning algorithms needed more features. And feature construction is a very important, meaningful way to add to that, but you have to be able to inspect the features. And so, back 10 years ago, when we were looking at aircraft engine data, it was very common for the engine to record a few averages during the takeoff, the cruise, and then the landing. And that was very typical. The data was there, it was being sensed, but it wasn't the practice across most industries to record that, and for machine learning people to use the raw sensor data. It was usually something like this. And that's what, what I came in and started working on, among other projects. But now today, we get something to this order of magnitude. And this is just a selection of the features of the variables that are being measured off of an aircraft engine. Most of these are being measured multiple times per second and constantly streamed. And the communication networks are such that this data becomes available rather quickly after flights occur, and sometimes you can even get them during the flights. And that's just for an engine. It doesn't even speak to the larger system of the aircraft. There's an interesting study recently that only 0.5% of the world's data is being analyzed, and I think in industry that's very true. And when you look at a set of data like this, you can understand why, is that yes, you can sense a lot of this data, but you have to know what you're going to do with it and how you're going to turn that into something meaningful. And that's this shift is occurring across industries. If we look at, this is gas turbine, for one gas turbine compressor blade, which is these little guys up in front here, would we monitor that, just kind of normal monitoring, you can produce about 500 gigabytes of data per day. And so when you think about all the data that's there that can be recorded versus what you have to turn, or how you can turn that into something that's meaningful, that is what I see data science today. It's addressing that gap of hey, we could record this data, we have this data, we have recorded it, now let's turn it into something meaningful. And certainly, as you are well aware, that when you go to actually put these things in practice, if you don't have a meaningful value story about how you would turn that into data, the cost of the IT infrastructure, the communication networks to just move this data, to store it, and then the labor involved in processing it, all comes into question. You have to be driving at what's the value that you can turn this data into. And right now we're in this midst, in a society of trying to figure out of all the data, all these digital representations of the real world that we produce, where are the biggest value plays? And that's, I think, the role of the data scientist. When we look at across for monitoring, now this is, again, this industrial perspective. This is a view of what GE looks at in terms of our remote monitoring and diagnostic centers, where if we take gas turbines as an example in Atlanta, which we work quite a bit with, where they have about 1,500 heavy-duty gas and steam turbines being monitored there. Those turbines are located around the world. The company we sell those, we make those turbines, sell them, and then provide the services, the data streaming into the center, and that happens for many, many different kinds of assets and customers. The challenge of how do you first move all the data, but then turn it into something meaningful is a big challenge. The second thing that we see happening, the second sort of major trend, is the industrial internet, or the Internet of Things, or the Internet of Everything. And I won't spend time on this because I'm sure people by now are very well aware of it. But something is changing. Something is changing in a dramatic way, that when everything becomes connected, a lot of how we deliver services can be done in very different ways. Analytics can become, can play a different role, from describing to being much more predictive and changing and working directly with control systems. There's all sorts of interesting topics. Artificial intelligence is a core, I think, a key technology in this vision. And what we're doing now, largely is how do we get all the pieces in place across that. And then the last thing, which is where we typically think of data science, is turning that data into some kind of analytical outcome. So taking our knowledge about the industry, our learnings, and this data, and driving it into some kind of expert system. So a few years ago, when we started this kind of journey, and I mentioned the software center in the Bay Area that we created, we did some work to identify the value of these markets. And this comes back to my point about having to make sure that you're going into these spaces and you're spending your time wisely. The savings that are, the value that can come out of this is tremendous. And these are just a few numbers, and they're very large and mind-boggling. But the message is that we're running all these operations and industries very efficiently today, but with the insight that we can get with some of this low-level data across multiple sensors and things, there's still an immense opportunity. And so this hopefully motivates people to think about some of these commercial industrial applications where they could really have major impact in world societal issues by driving these efficiencies. So that kind of motivates what I wanted to, how I wanted to set up this discussion around knowledge and explanation for data science. And the key there is that the world is changing. There's an expectation that data scientists are going to provide value from all this data. Companies and industries and governments are taking the bet of storing this data, and they are creating these infrastructures. We're creating the big data centers of excellence across the world, and NIH is doing a ton of things. All the institutions are doing things. And now there's, it's kind of data scientists, bring your A game, and let's, start getting value out of this. And so when I look at that problem or that challenge, a couple of things from my experience kind of pop up and makes me, think about, okay, if we're going to be successful here, there are two things that I think we really need to start looking at. And, if I had my druthers about where to invest long-term research and encourage the data science community to go in these ways, this is what I'm stressing today. So the first point is knowledge. So data science process. These charts are, everywhere across the internet about what is the process of a data scientist. Really, if you look and compare those charts, they're pretty much the process, what we used to call KDD a dozen years ago, knowledge discovery from databases or from data. And, it's a very typical thing in machine learning. It's, get the data, process the data, clean the data, do some analysis, do some modeling, visualize, and get to some decision. The rule of thumb is that up to the modeling point, you spend about 80% of your time in getting the data and cleaning it and doing your initial analysis. And then the last 10, 15% is actually doing the model building and then visualizing. And all these discussions today around data scientists, and I love this term I heard recently called the unicorn, which is like the mythical data scientist, that nobody has all the skills to do this, and data scientists are really teams. It's a very interesting kind of discussion about skills and labor. The point I want to make here is a little bit of a shift or a little bit of a change in perspective on this process. So this process is, I'm not debating that it's something like this. My point is that in the real world, when you get outside of some of the trivial examples that are used in communications around data science and machine learning, when you get to real world problems, the reality is that you usually start with a domain expert, and they're the ones who get you data. They're the ones who know the domain. They're the ones who know what the problems are trying to be solved and how data can be used to solve that problem. And so that domain expert gets you the data. That domain expert also usually does initial data processing. They also usually do a fair amount of data cleaning, and then they hand off to the data scientist, a MATLAB file, a CSV file, a minimized representation of the original data and simplified representation that an analyst can now go and build models out of. And then that person works to build their models. There's some revision, some exchange with the domain expert to clean up and understand the data. And then it comes back to the domain expert. And the domain expert looks at the data and they validate. Are you showing me? Does it make sense? Was there some anomaly in the data? Was the data that I gave you representative of what I thought? Do your equations or does the predictions that you're making make sense to me? Do I see confidence intervals that are appropriate? Is there robustness so that I can now think about how do I turn that into a solution? And then again, it's the expert, the domain expert, that then works to turn that into some sort of solution that understands the domain. Maybe it's the machine, it's the system that the solution, the data science insight is going to go to. So I would look at this data science process and I would layer underneath it these three stages: the knowledge acquisition and synthesis, the explanation and the validation, and then finally get to solution. We all want to drive to solution, but if we don't recognize that this first part of the knowledge acquisition and synthesis is a time-consuming but critical task where the reality is that a domain expert does a lot of that upfront work. The analytic model builder person or the data scientist has multiple conversations. They learn enough domain knowledge that they can so they can start to build models. They iterate with that person over and over again. And then they have to go back to that domain expert to validate their findings, who then takes it. If we look at it with this perspective, it really, I think, starts to, in my opinion, form a better grounded view of the data science role. And you can really think about it in two ways. One, domain experts probably start to take on more of the data science task. But the other way is that we need to think of how do we help the data scientists go after all this data that exists out there where they can start to address this knowledge acquisition and synthesis phase without having to have so many conversations with domain experts, which, their time is very limited and valuable. And that's where this first knowledge piece fits in. And then the second part is the explanation piece. So, let me talk just a minute about raw data. A lot of times I think from data science and especially my sort of initial learning coming into this environment is that, we think of data as spreadsheets, of, data files, of MATLAB files, of, tables. And the reality is that the data that we need to start thinking about, it comes from things like this. It comes from physical things that are very complicated, that took, generations to optimize and to create, and are, individual in themselves. Different units, different engines like this will have different data signatures themselves, and they're all very unique. And, a lot of these wires and cables and pipes going around these are some of the sensors that are on this engine. But the engine itself, how it's used, the environment it's in, the state of the sensors, the manufacturer of the sensors, the wiring, those all have input or impact on the actual data that you get when you go in to do your model building. And a lot of the data that, we think of as, coming from an engine is actually derived calculations based on physics models, that you have some real sensors that might be measuring temperature, pressure, or vibration, and then there's some calculated sensors or calculated values that get created from those ones that end up in a spreadsheet. And so as a data scientist, it becomes a very complicated, journey of trying to understand what this engine does, what are sensors measuring, where do they located, what's the impact. That's when I talk about domain knowledge, is one of the challenges or the really hard things that you have to get right at the beginning if you're going to do something meaningful downstream. And data processing itself it's a, I mentioned the kind of rule of thumb about you spend around 80% of your time in that data collection and processing phase, is that, you need to understand the domain, and you need to start to understand this data. And every time you make some change to it, it increases the complexity of the overall process. So, this is why it's very difficult to do like data cleaning. The expert often does a lot of the data cleaning, because you might have different like pressure gauges that have some weird kind of behavior that they, like cycle back on their values every so often to just like clean some system out or something. And if you don't have the knowledge of that particular sensor and who the manufacturer was and how it measures something, it's really impossible to do that cleaning. And so this complexity of constantly kind of taking original set of data, making twists and turns and changing the shape of it, is not a trivial job. That probably, along with the acquisition of knowledge, is one of the most important things to get right. The modeling, in my view, is important, but a lot of times we can get simple models once we do this first step correct. And that leads me to this kind of observation, which, I will admit it's not the most super rigorous in terms of the function shape here. It's an estimate of what I think, or what I kind of believe. And I'm trying to be a little controversial here, and because I think this sort of goes against the current kind of state of thinking, is that the more kinds of data and the sizes and the speed of data that you're given, or that an organization, industry is confronted with, the more domain knowledge is required to work with it. And why do I say that? So if we think about the aircraft engine example, a lot of people who are working and building models, kind of as a data scientist role on that data, would have been working with fairly cleaned data. The aviation engineer, the aviation expert would have got the data from the engine, put it into some database, cleaned up values, dropped off the first, rows and the ends rows where things were going weird. They would have added a column that tells you if it's at cruise or takeoff or lander, and they might have truncated the data for you so that you only have cruise data. They might have ruled out certain flights or legs that engine's flying in because of it's flying in, maybe intense heat or in conditions where there's a lot of atmospheric challenges. So they give you sort of clean data. And we would work with that, and we have to get, some domain knowledge to work with it. That was what it used to be like. Today, all the raw data is just going into a big like Hadoop store, HDFS store, or whatever your organization's using. And so now you're working with the much rawer data. The challenge is much harder to figure out that domain enough so that you can clean it, process it, and get it ready to do some modeling. The other thing is that the expectation is that with more data, hey, we're giving you all this data. You're a data scientist, go find something meaningful out of it. Well, the more data that you give somebody, it's much more challenging because they have to, weed through all those issues. And the systems, whereas before you might say, okay, I have a vibration sensor that we're going to give you to measure from this engine? Can you go and figure out a way to build a virtual sensor for vibration or to predict something about the state of the engine from vibration? Well, today we'll just give you vibration, exhaust gas temperature, we'll give you all kinds of pressure measurements, and now can you do something about vibration? So the systems increase, and of course then there's all these kind of feedback or let's say interactions that are in there. So with more data that's coming, you have to have more domain knowledge, and it's increasing, I think, dramatically as that data size increases. So how do we address that? Where do we find the knowledge that we'll need to, as data scientists, to accomplish these tasks? And you know, in the industry, you know, several places that you'll see this, and I'm pretty sure, you know, it's, when I say industry, I include healthcare, and we'll see this in lots of similar places. You know, have experts documenting as a byproduct of the process things like from their emails, case management systems, customer reports, things that are sent to customers, maintenance logs, different manuals that the organization or the OEM provides or guidelines, and then of course the expert's heads. So you see that whereas, you know, we do have this written logs of knowledge that is captured in all these places in an organization, we also have the experts who are doing that work as kind of an audience that we can go and interview. So how do we get that knowledge out of those places to help us understand domains and help us do data science? So here's an example, and this kind of, you know, is how I think there's a massive opportunity around knowledge for data science, is if we have an expert and he makes a statement, and maybe it's written down in a email or a document somewhere and stored in the organization. Whoops, sorry. He says something about Abraham and Mary and when they're born, their child, and in his head he has this kind of graphical model of the world and how people are related. This is very, very important. This is an essential piece of knowledge that you want to have about the asset and how things are related to each other. We could think about giving that knowledge to somebody in this sense, but that's not very nice. It's hard to understand language. Language is by necessity imperfect. And so if we think of something like OWL and the semantic web, we could give him an OWL model. Well, that's not very easy for him to understand or for somebody to understand. But we think that the semantics, and especially the semantic web, is a really interesting way for us to start capturing knowledge across organizations and have data scientists use tools that can leverage semantic web technologies. So we developed something a few years ago called Semantic Application Design Language, which is a natural language-like representation for capturing OWL models, where you can make a statement like this that is quite readable to a person. A domain expert, and we validated this, can write these themselves instead of capturing the natural language text. They can write the description of the domain or the rules or the data and the properties and the relationships in a text-like representation, which is actually a formal representation that we can map directly to OWL and use it in all kinds of things. Two of them, which we've had a lot of success lately, is for doing unstructured data analytics, which is essentially text mining and extracting knowledge from textual places using ontologies and using this captured domain knowledge. And then also, of course, which I think is a near term, but it's probably as big or bigger opportunity, which is ontology-based data access. So moving away from the traditional relational storages of data, which we've already started to do with HDFS, but layering on top semantics to give all that HDFS, all that big data meaning. So here's a few references where you can do some more reading if you're interested that I alluded to earlier. So one of my colleagues, Andrew Crapo, and I have a new book chapter coming out hopefully later this summer around our semantics, a breakthrough thing, and I'll give you a sneak peek that the answer is we think it is. Then some earlier work around the semantic application design language I mentioned, and then lastly an example of the text or knowledge extraction from text using captured knowledge And the thrust with these things here is that if you capture the knowledge from the experts in an ontology or in a formal representation that your tools can now leverage, you can start to minimize that knowledge acquisition and synthesis phase and start to unlock more opportunities for data science to be successful. So let me move to the second part, which is around explanation. So I mentioned at the beginning that AI is what sort of drove me into going to grad school. So I played soccer quite a lot when I was younger, and when I was in graduate school or undergrad, I started getting interested in some of these competitions called RoboCup. It was very first beginning years of them, and if you're interested in that, Manuela Veloso, who was just highlighted in an IEEE magazine for her contributions to the RoboCup competition, was one of the big figures there, and Peter Stone, who's at UT Austin, Veloso's at CMU, were publishing some work that I thought was really interesting, and as an undergraduate, I thought this is really kind of cool. You have, like I play soccer, the strategies to play soccer are quite complicated. How teams move, how players move, and then think about robots doing that was really a kind of compelling thing. And so I started to do some master's work with a professor at the university around could we learn strategies for robots to play soccer, and what would that mean? And so if we think about that problem, it's really fascinating because it's a complex problem. But what if we learn something like with the neural network, for example, and we can demonstrate that the soccer players do something meaningful and they play this game and they win it, okay? But now we want to go and put that into one of the humanoid, the DARPA humanoid robots that's maybe like, I don't know, it's probably tens, hundreds of thousands of dollars. And we're going to have it run around on a real field. And hey, if your neural net doesn't account for like when it comes to a corner and the robot just keeps plowing ahead into the wall, hey, that's going to cost you a couple $100,000. So what happens if you have to understand the strategy? And so that's what we started to look at. And that comes to the second point of data science, or this kind of second challenge around explanation, is that as we see the data-derived insights that data scientists can make from data increase in an organization over time, the time that we're sort of required to expend to validate those insights to turn them into impact increases dramatically. And and there's kind of two main reasons that I would say that I believe this is true. One is that we're not going to be increasing the number of experts. Again and again in different industries, there's a shortage of experts. Oil and gas industry is one where they're facing a lot of retirements. Petroleum engineers are in high demand. So we're not going to scale the number of experts to the same scale that we're going to try to get insights out of data from data scientists. Those two aren't going to work out. So experts kind of going to stay the same. It's a highly constrained resource. But again, in industry, as you get data science and you get outputs coming, somebody's got to go and validate that it's a good thing, that it's a reasonable thing, that it works. And so as those things start to pile up, your time that you're going to have to be spending to validate starts to increase dramatically, and the systems themselves start to increase dramatically as you get more and more data. It's one thing to build a model that predicts one kind of anomaly for an asset versus trying to build a model that can drive a whole, like a robot versus one that drives a whole fleet of robots, and then one that drives or controls, a robot's interacting with humans trying to accomplish some big task. So that system and complexity increases dramatically, and so this is why I think here we have a major challenge that as we're embarking on this explosion of data science, which I hope is going to drive all this massive outcomes and values for our society, how do we face this need to be able to validate all those insights that will be generated? And that's where, I think about these in kind of two paths. So the top path is what I call the traditional data science path, which is the, one that's, like I said, traditional, but I'm being a little bit cartoonish here. So encoding a problem and the domain into some system like that a neural network would require, using some kind of near-optimal search method on that network to find the coefficients and the linkages and the parameters. And then the data science job is then how do you untangle that or convince the person that it's okay, that the black box works, they can trust it, how do you put the right V&V things around the system? That would be what I'd call this kind of more traditional path. In between here, you have things like association rules and decision trees, which you are very highly confident. It's a little bit, you can still use the same, you still kind of encode the problem, but you can inspect those and they have some, you can understand what they mean and it's better. Those have some more interpretation kind of capability. But down here is this kind of other extreme path, which I think is highly, highly interesting and have been kind of working in a number of years, and we're doing more and more in this space, which is describe the domain knowledge or the problem in a domain-specific language, especially one that the expert can understand and can do that themselves. And then you search that space using some algorithm and some measure that makes sense to you for that space, and then the domain expert can then inspect and understand that and validate it much more quickly. And so two methods, one that I'm going to talk a minute about is genetic programming that does that, and then there's some really interesting work around inductive logic programming, and then we're also exploring some reasoning capabilities like answer set programming to be able to show a result, but then also explain how the system got to that result. So let me come back to the soccer example really quickly. So in some of the early work that I did using an approach like this, where we wanted to learn soccer strategy for keep away soccer, which is a 3-on-1 task with the ball in the middle. So this simple representation, the ball is the number 4, the defender's the number 4, the ball is the 5, and these 3 offensive players are passing it around using an evolved strategy with genetic programming, which was it wasn't terribly difficult for it to come up with a strategy. But we can, now we can look at that solution and we can understand what it's doing. It's not the case that they're elegantly described solutions that you can, they're like super easy interpretable, but it's a lot further along, it's a lot closer to an expert looking at this and saying, okay, hey, I can make sense of this. And just by example, because I like to be, not to make it look like it's what it isn't, if you just look at this little part of this tree, this execution tree logic about what it does in this is one of the offensive players, this whole thing basically is saying, go to the ball, even though it has some other junk in here. If you look at this if then else equation, it's just the 2 options that it's going to execute is going to the ball. So you can take these big things and reduce them down into something that's more manageable. Then you can show that to somebody and say, okay, here's the control strategy that I want the robot to take. Is that sufficient? Is it, is it going to be safe and things like that? And so here's some references around the genetic programming example I just gave. There's a recent paper from some folks from my team around using semantics for inference and drug-drug interactions. That was from last year. And then I think some really cool work that I'm a big fan of is from Shamit Golwani at Microsoft Research around, in a similar vein, using declarative logic and inductive logic programming to learn programs. And he did a lot of this with Excel spreadsheets, and I'd recommend checking that out. And I also highly like this talk by Cynthia Rudin last year at KDD, where she talks about the value of like association rules and decision trees for making it machine learning interpretable. And so the last thing I want to highlight is an example of a application that the team here just did that was highlighted at the HIMSS conference. This big healthcare IT conference was released and is having some great success and publicity. You can just Google denials IQ to read some of the press about that. And what it's doing, it's using the same approach that I just described, and that's kind of the thread of things that we're doing, the pattern that we're trying to use in some of our data science applications, but also as we develop data science tools, is that, embed knowledge and then use techniques that have explanation capability, so that we can get to insights and action faster. So in the U.S. healthcare spending is around almost $3 trillion. You're very much aware because you participate in the healthcare system. The doctor sends in claims to insurance. A lot of them get denied. The denial rate's around 5%. And so how do you help a provider go through those denials and get paid for their services? So traditionally, they would go through all these claims and look for patterns that are based on their experience and intuition and go to try to dig into that. But that left a lot of things unanalyzed that they just didn't know what to do with. And a lot of that is kind of left on the table. Some claims are just ignored. They never get the payment. That causes inefficiency in the system, which drives up costs in other places. So it's a big problem. And so what we did was to start to think about how could you capture some of that domain knowledge about the healthcare process and this denial process and get that into insights to the experts faster so that they can take action out of it. And so we developed an approach that's part of this denials IQ system where patterns, we start to identify them automatically, and then we use the semantics of the domain to group them into themes that are across a couple factors like surprisingness and have the ability to be addressed in the types of processes that they can go, like what kind of capabilities does a particular provider have that they can address some of these claims, and grouping those in such a way that they can very quickly take action on them. And that's all done, not as here's a data scientist looking at your data, providing it, and then now I'm going to show you a report. It's a tool that does it automatically by itself, so the person that was doing the claims before now goes and uses this tool, and the tool itself is saying, here are some of the patterns, and the users the feedback is that, hey, this is a very effective way to understand what's happening in our denial process that we can take action on right away. So my main 2 points I want to leave you with from the data science is, one, hopefully you got an understanding about what industrial data science, some of the challenges and things that we're thinking about and that we're faced with. But two, the knowledge part, when we think of knowledge as part of the data processing stage, that can really help us scale that acquisition and synthesis phase, which are where we end up spending a lot of time. And frankly, because of the lack of experts, is where I think a lot of data scientists will get hung up. If we can start to address that and get data described in meaningful semantics using tools like ontology-based data access on top of some of the big data systems, now we're starting to short-circuit that process and get to do some more meaningful work sooner. And then the second piece is that we want those light bulb moments. We want the light bulb to click on as fast as possible in a meaningful way so that action and impact can be had. We don't want to just create charts and find interesting clusters and things. We want to get to action. So if our models can't be explained or interpreted, then we've set a higher bar for us to get to the action. And so by looking at methods that have explanation as part of what they do, then you can get to understanding in a much faster time and start to address what otherwise could be this kind of exponential increase in the time that's going to be needed to address all these models or all these insights. So those are the main points from today, and I thank you for taking the time and sticking in there and listening, and I'd be more than happy to try to answer some questions if anyone has any.
Yeah, and if you guys have questions, you can either type them in the window or you can just mute yourself and ask the question, whichever works best for you.
So, Steve, this is Stan Ahold. I do have a question if you don't mind me posing it.
Oh, sure.
So, first of all, I really appreciate your presentation, and I think it has particularly some pieces in it that the folks here at RENCI will benefit from. So I want to go back over it at a future time and make sure we read some of the papers and come back to you to ask more questions. But one of the things that strikes me is that we are also running into this problem where the additional metadata that we need to be able to shorten the 80% of the process is not there. And so I'm curious as to whether or not you have a relatively high degree of optimism about ways of building tools that automatically extract and associate metadata with the raw data. Do you think that's is it something that's doable, or so idiosyncratic it's just on a case-by-case basis?
I think it's completely doable. You know, the experience that we've had is that you're displacing a current process about how data is collected and how the operation works. You know, once you get some critical mass going and you have, you know, the initial kind of metadata approaches cemented and being used, now, you know, the other data that comes in where you're missing stuff, it tends not to look so dramatically different from what you've seen before. You know, so then now you can start to be able to automatically identify variables and lock them in. And there are some tools out there today that from a generic kind of consumer point of view can do that very effectively. You know, if you enter like a typical, you know, set of data about people, it can recognize names and dates, it can run all kinds of classifiers and start to recognize entities and auto-label table things. You know, so there's a lot of things that are happening what I'd call on the structure types of data. Now when you go into the kind of more numerical types of data like sensors and what a lot of really industry is about, it's a little bit more challenging. But I think once you have a critical mass, now it's much more easy to compare because things aren't so different. You know, like give examples that if we have like, let's say 2 different gas turbines or 2 different aircraft engines, they more or less are going to have a lot of the same types of measurements, but the locations, the variable names, the columns that you find those in are going to be very different. Everybody will have those wired up differently. But you already know kind of what you're looking for, and then you can start to compare actual sensor values and start to realize that, okay, with these ranges or the frequency of measurement or the behavior of the wave, you know, it's most likely something. It's most likely a particular variable. So I think once you get that initial set of data going, then the job becomes much easier. But hopefully, you know, as with all sort of data quality issues, the more that we can do at the source, so the more that we can enable semantics to be captured by the data creators at the source, the better. And that's really why we have that semantic application design language, is that we want the people that know the domain who are describing it to write it in those ways so that we get really meaningful metadata at the beginning.
Okay, that's very helpful. Thank you.
Okay, do we have any other questions? You can either type them in, or I suppose if it's just one person, go ahead and talk. Anything else? I don't think we have any other questions, so if that's all, once again, thanks to everyone. Wait a minute. We have a question. This question is from Steve Hayden, and the question is, can you describe in more details of usage of genetic programming?
Oh, sure. So I guess, is this a question that's emailed, or is this a chat question?
It's a chat question.
Okay, so while I'm talking, I guess one is the usage in terms of how we use it specifically, or how one uses it I would ask back. So if you can clarify.
The question is how are you using it? How you use it?
Okay, so actually I forgot to put one reference in here. I have a book chapter that will come out later this year that looks at genetic programming as a tool for data science, and I presented it at the Genetic Programming Theory and Practice workshop in Ann Arbor a few weeks ago. And so I'm using it and have been using it for the last decade or so as a modeling tool. So for a number of years I ran a workshop called Symbolic Regression Modeling at the Genetic Evolutionary Computation Conference. Last year was the last year that I ran it. I think it was for 7 years. And it's really and if you're interested in this space, interesting fact was one of the people in the community was named by Forbes like one of the top data scientists, I think, in a few years ago. His name is Hod Lipson from Cornell. What that work does and what I focus on is, finding nonlinear models out of numerical data. And I think it's extremely effective technique for doing that because you immediately get to a function and the form and the coefficients that fits data. And when you're doing data fitting, the user can immediately look at the fit and look at where the residuals are, but they can examine the functions that you're creating, so the mathematical kind of nonlinear functions, and start to mentally quickly kind of say, okay, is that meaningful, or are you finding some kind of weird anomaly in the data? And so I've been trying to drive the research community and contributing to it kind of more from a basic point of view, but then internally I use it as one of several data science techniques that when we're looking at data and need to model it, to run it through a genetic programming system for symbolic regression to see what kinds of models I can produce. That is, if you look at this kind of pathway of different modeling or machine learning things here, as you go from like logit kind of regression techniques and you start to move more into the nonlinear space, instead of maybe using like gradient boost regression or random forest or a neural net or SVM, I would kind of try a genetic programming approach because I can very quickly go back to the expert and say, oh, here's the functions I found. Do those make sense?
Okay, and a follow-up to that question is what specific problem domains are you addressing?
Well, so the easiest question is using that particular technology, I've looked at many different domains in GE. So we do research for all the GE businesses. I have done a lot of work for aviation and power and water and oil and gas business. And so over 10 years, lots of opportunities to apply it in different places. So this, the paper I can put a link somewhere when it comes out, speaks a little bit more in detail about some of that.
Okay. Any other questions? Going once, going twice. Here's another question. Steve, are there data sets available for students and researchers to explore in industrial data?
That's a great question. And, so today I'm part of a steering committee around data sharing underneath an NSF called Big Data Innovation Hubs, which we're trying to look and come back with a position and sort of a strategy around specifically data sharing. So one is there are, repositories of data that come from industry that are out there. My point of view is that it's way too hard to get those out for a lot of very good reasons. And there is also the challenge of, as data science and the data-driven business continues to grow, the value of the IP and the insights that somebody might find from data increases and makes this whole thing more complicated. So that's why I don't think the answer is that we need like file sharing systems for people to post data. We need to solve this in a more fundamental kind of core way around how do we make a data available so that tools can be improved, industries benefit from those tools being produced, but they don't suffer from giving out some of this critical data, which, the businesses will become running on that critical data going forward. But, if you're interested in a particular kind of data, there's lots of available data sets that represent those different kinds of industrial data that are available, scattered around the web and things like that. So if you have some specific ones, I can try to help point you to.
Okay. I don't see any more questions. Let me remind everyone that the webinar will get posted on the NCDS website. It usually takes us a few days to get it up there, so check that out and check out previous webinars there as well. And once again, thank you for attending today's webinar. Thank you, Steve Gustafson, for a really interesting presentation on AI and the industrial internet. We will be taking the month of July off from our regular monthly webinar series, and we'll be back in August, and we'll be sending out information about that talk soon once we get everything set up. Also, please, if anyone is interested in diving more deeply into big data issues, there's still time to register for our Data Matters short course series, which is co-sponsored by NCDS, the Odom Institute at UNC Chapel Hill, and RENCI. So you can just go to datamatters.org to register for that. That's taking place the last week of June in Chapel Hill. That wraps up the webinar for today. Once again, Steve, thank you so much for your time and your sharing your expertise. Everybody else, we hope you have a great day, and that's it. Okay.